I went live like 2 seconds earlier today. Usually I just hit it on the clock marker. Not that you'll realize that. I'm just waiting to make sure I'm live and my audio is going through. I don't hear myself yet, so I'll just refresh the page. Awesome. I can hear myself. We are live. Welcome back, everyone, to the study group. Let me figure out which tab I want to look at. This is the right one. We are going through this book in a mixed fashion. So I tweeted out that we'll be going through the implementation of attention and transformers today. That is because it's the third chapter in the book, if I remember correctly, third or fourth. It's the third one, and we were supposed to go through this last week, but I sort of went on this tangent to explain what attention is, and we spent a good amount of time understanding what attention is, how we as humans pay attention, and how dot products of different things can make neural networks and transformer models pay attention to different things. Now that we've done that, we'll be, we'll be going through the implementation, and one day I will ban Ayushman from the stream for mentioning coffee. Anyways, I have one more announcement. I'll be giving away one digital copy of the book. Thanks to the authors who set it up. So anyone who's active in the chat, I'll just give it out to them. And Dylan, if you're watching this, I'm still waiting for your email to send you the free copy. So please reach out if you have. If you haven't, if you have, please just ping me again. I might have missed your message. Hey, bro, great to see you in the chat, and good morning to Les. Hey, Pastor. I've been seeing Pastor write about the group. So this is one thing I want to quickly highlight, that Pastor has very kindly been sharing his learnings, and I just recall that. But you all should check out his stuff on LinkedIn. He's been sharing what he's been learning, and I find his writers very well written, and they're really nicely condensed. For example, he's explaining self attention here, and I believe Pastor, you've written another one, right? Anyways, you can connect with him on LinkedIn, and I encourage everyone to just also take some time to write such explainers, because it also sends a signal to everyone that you're learning about this stuff, and it also, at least for me, the reason why I do any of this is it also helps me understand stuff. So end of speech. um, hey Murli, and someone saying good night. I hope you have a nice sleep. Cool. So now we'll come back to the slides, and I'll quickly recap what we learned last week. We paid attention to a lot of attention articles, all puns intended. We looked at what the transformer architecture is, how that works, what are query key and values. Someone has called me a chai master. I'll accept that title. We looked at what query key and values are, and inside the book, I'll refer to the book for this, but they refer to query keys and values like so. So let's say you're trying to buy ingredients for a recipe. Your ingredients are the queries, and the items that are present are the values. Sorry, are the keys, and when both of these match, you get the value. That's how they explain it inside the book. They have like they again explain it in another way later on, but generally what's happening inside the neural network is it sends a query to some text. If it matches with the key, you'll do a dot product. If it matches with the key, you'll get a higher number, and that basically means that's the value you care for. So all attention models and all transform based models are based on this architecture, which works on query keys and values. And don't worry, you won't just see me shake my hands all day. I will go through the notebook and understand how this works. How much math do we need to know for learning transformers? None at all, except from the fact that you need to just know how matrix multiplication works and how dot product works. If you don't know that, it's fairly easy to just do that inside a Python notebook as well. Where can you find the notes for the past week classes? There are no notes, but on the channel, I've created a playlist, and you can check that out if you want. So if you head over to the channel, it's right at the top, and that's the Hugging Face study group. My humble opinion is none if you want to use it programmatically. For a deep dive, you need linear algebra and calculus, definitely. Yeah, but like for as Jules said, for getting started, don't worry about it. And once you get to the stage where you really want to fiddle with the models and you're like trying to solve problems, trying to solve Kaggle problems, at that point you're already like an advanced user, and that should be exciting to you. So yeah, yeah, this is open to everyone, as I've been trying to mention. Um, so I looked at getting started with NLP notebook, and this was by Jeremy Howard. So today I'll first of all finish this notebook, and then we'll go back to the other stuff. We also looked at another notebook which I'm yet to finish. It's called Iterating Like a Grandmaster. And my goal with all of these study groups is to somewhat provide you with additional material outside of the book, because I assume everyone and everyone can read the book. But if you are spending time watching this, maybe I can provide some extra value to you all. We also understood how multi head attention versus self attention works. And we had looked at encoder decoder architectures. We had looked at families based on encoders. So if you remember inside the notebook, and I've cloned the notebook, someone had asked me earlier, where can you find all of the code files? Just go to transformersbook.com, and under the like button you usually find all of the resources. So if you go here and click to download the books code, it will take you to the repository which I've installed here, and I have all of the notebooks. So inside here we're looking at notebook 3 and 4. At the end of the third notebook, you can see the families of transformers. So some are just encoder based, some are just decoder based, and the ones in the middle in white boxes have both encoder and decoder architectures. I suspect these can be like good interview questions as well, so it's also good to know all of this. And I've been mentioning for a while that I will keep publishing questions to our community forums. So if you are interested in trying to learn through them, you can just sign up here and consider introducing yourself. I see a bunch of new names, that's why I went through the regular stuff one more time. And then we also looked at what are both of these good at. Last week, this was misspelled to casual. It's not casual, it's causal. So families based on decoders are just causal or autoregressive. And the families based on encoder have bidirectional attention. So this is causal and not casual, as someone had corrected me in the chat last week. So these are the type of questions I'll be releasing. At least I like to learn by doing this, where I create Anki cards with all of such questions and I keep iterating through them. So if you want, you can just take a screenshot right now and like try to answer them by yourself. And at the end of today's live stream, you'll be able to answer all of these questions. So if you want, you can still again take a screenshot right now, or I will be posting these later on through the forums where you all are welcome to join and discuss. Cool. So let's get back to this notebook, which I'll quickly re-summarize. As I remember correctly, we've gone through all of this. And if you are new to Kaggle, all you have to do is just go to kaggle.com and you can search for different stuff here. So, for example, this is titled Getting Started with NLP. And what I'll do is I'll just put in the title. And this should take you to the book. So inside this book, Jeremy Howard has introduced a lot of things, and he's also talked about Kaggle, but we've already gone through this, so I'll keep skipping past that. The things worth remembering: documents in NLP are one of two types. Larger documents have one text file per document, and smaller documents have one document per row in a CSV file. This is how this competition was structured, and we'll just look at the competition in a second. Ayushman is considering generating art with the following prompt. I'm telling you, the model will crash if you put my name and coffee together. I can guarantee that. So this is how the competition is structured, and many a times this is how you'll find such CSVs as well. What are smaller documents? Uh, like a Bro is saying make sure it works. A good rule of thumb is if you open the CSV file on a laptop, it should open and not crash your Excel program or whatever you use to view it. So that's my vague rule of thumb. But generally, a large document is like if by itself, let's say this would be a TXT file, it's going above 2 megs or 2 megabytes. That usually I would say is like a large document. And in such cases, these files can be larger than that. So inside this notebook, we looked at the data set. We also looked at how we can represent such data and how do we concatenate different columns inside pandas. We learned about tokenization. I'm just refreshing this for everyone. And inside the notebook 4, it's again re-mentioned in a bit more depth. So we'll just take a look at this. But for fresh refresher, tokenization, transformers use a dataset object for storing a dataset, and it's stored like so, so it has the features and number of rows. The challenge with all of this is you can't pass words to a neural network because you want to do matrix multiplication, and you need to convert these words into numbers. So tokenization splits each text into words or tokens basically, and numericalization converts each token into a number. A bit more detail now. Let's take a look at this. So this is what the tokenizer pipeline looks like. The following 4 steps happen, and when do they really happen? You honestly never find out, and you don't realize it, because what you're really doing is you're doing auto tokenizer and you're just importing the name of the model you're concerned with, and after that you just go auto tokenizer dot from pre-trained model name. That takes care of everything. So when do you really care about the tokenization pipeline, right? Like if all of this happens like so, where you can just import auto tokenizer and you can pass a model name and it should take care of everything, and you can grab the tokens like so for Jack Sparrow Loves New York. When do you really care about all of these steps? It's when you're working with a custom application and you really have to look at what's going in and coming out of a model. So most of the times, for all cases, auto tokenizer auto model is a really good starting point. But then, for example, I will mention one example where you can't like use off the shelf models. And since I see Ayushman and Nischay in the chat, all of us had teamed up in this competition, and I learned a lot from all of them. So this competition had a goal of predicting the relationship between code and comments. So it had a bunch of Jupyter notebooks, and what you were supposed to do were you had all of these notebooks with different cells inside them, and you had to construct a way to order them. Whenever such a task comes up, you can't just do auto model, right? You have to do like a lot of stuff, and at that point you also need to know how tokenizers work. So that's what I was getting to. Most of these notebooks were Python notebooks, and Python is case sensitive. Python has these symbols that carry meaning, right? So you don't want to just discard that. When you're working with English language, a lot of these tokenizers discard that, right? As they should. But for such cases, you should be careful about that. So there were different models to deal with it, and you have to like be very careful about that. Let's take a look. Search for code, we can see there's code bird base, and this has pre-trained weights for code bird, which is a pre-trained model for programming and natural languages. It was trained on this data set. Uh, Enough details. If you want, you can look on the channel. I live stream about Kaggle every Sunday. But this is when, or such examples are when you really care about the tokenizer pipeline. So the following steps happen inside of it. You have some normalization, which means you have a sentence, and once that goes into the tokenizer, it will remove the white spaces. It will maybe convert everything to small case, or maybe also remove some special characters. So that is normalization. Then some pre-tokenization happens where it's let's say it converts everything to Unicode. For representation, so on and so forth. Then you have the actual tokenizer model, which takes the sentence and converts it into this. And after that, sometimes you also have post processing being applied where you could have special symbols being added, so on and so forth. So that is how tokenization works. And we had looked at this at a very initial level. Now I wanted to revisit it and explain it in complete sense. Realistically, most of the times what you're doing is from auto model or auto tokenizer dot from pre-trained, you pass in the model name, which in this case is Roberta v3 small, and then you can tokenize any sentence like so, and you can also print it out to see how that works. There are special tokens for different tokenizers, and you can learn about all of them. I'm looking at the chat and I'll just answer the question after I wrap this up. To learn about them, and this is covered in the chapter 4, but I'm sort of spoiling the chapter, not that it's a movie. Special tokens is what I'm looking for. Sorry, I'm just trying to find the line where special tokens is disabled. I had that line open, but I scrolled past it. So now you're stuck with this. But whenever you're working with tokenizers, you can usually take a look at the special tokens and also print them out explicitly. Once I quickly find that, if I do. I think we'll come back to this, so I'll again point it out. But inside the tokenizer function, you can simply print out how the special token works, and these are usually end of sentence token, class token, SEB token, so on and so forth. And these carry a special meaning towards the model. So that's when also you really want to care about what's going inside the model and how the tokenizer works. And this varies from different tokenizer to tokenizer. So that is what auto tokenizer takes care of once you import that. When tokenizing, they assign numbers randomly. So what you are thinking about Abror is an embedding. That is something else. But when you are tokenizing, all you care about is constructing a mathematical representation for your input sentence. So that is what's happening here. And what you are thinking of is embeddings. Summer is there. Yes, summer is there. I also have all 4 graphic cards running, all 5 rather running at full speed. How will pre-processing technique help in tokenization and later in model development? So like I just pointed out, let's say you're working with Python code and you're like trying to create a replica of, I don't know, code GPT or the model I just showed you. There you have to care about what language you're working with, how does Python behave, does your tokenizer align with that or not. Does the tokenizer work with every model? Abror has kindly already answered this, but as he said, it varies from every model. And in the first chapter, the authors had pointed this out. And I suggest you should do this experiment. When you have such questions, it's like the best to just load up a notebook and try it yourself. So load up an incorrect tokenizer to another model. Like try to load Bert's tokenizer to Deberta and see what happens. It's like you put someone else's brain in another person's body. It just doesn't work. That's what happens. That's like the most simplistic answer I can give. But all of these models expect a certain type of tokenizer. Sometimes they can be similar. Most of the times it's like quite different, as Abror pointed out. So we looked at how tokenizer converts all of these into special representation. Now the model is trained on this and it understands how this works. So underscore would carry a meaning here. And when it's looking at such tokens, it would look at underscore in a different way. And also split words that are uncommon into like their subparts. And someone was just asking that how does tokenization work? So this is the simplest function you can think of, and then you can map it and run it in parallel. I'm working on an Jax implementation. That is really cool. Please do send it my way or post it in the next study group if you want. And if you want, we can showcase that in the next live stream during the first few minutes. For those that are curious about Jax, it is quite a challenging thing. So leave that to Tarun if you're new to Jax. It does take a while to get used to, especially if you haven't done functional programming. I haven't. I have strong opinions about how I feel about it. So we have tokenized all of this, and this adds a new item to our dataset called input IDs. And then we can take a look at all of this. And now we've successfully converted this into numbers. So we have all of these numbers that are representing this. What are these IDs and where do they come from? The secret is there's a list called vocabulary. And in the tokenizer, it contains unique integer for every possible token string. And you can look them up like this. So you can simply do a dictionary lookup and you can see what number it is. So inside my dictionary, you'll get an out of bounds for coffee. I don't know if Ayushman is still watching. Afterwards, in this notebook, you learn how to set up the validation set and go from there. But that is all I wanted to refresh about tokenization. Now, this notebook is a good one because it teaches you how to iterate like a grandmaster. I promised in this live stream we'll take a look at the implementation of transformers. We will after I cover this, and after that we'll also take a look at how to work with tokenization and multilingual NER. Before that, this is like a bonus out of the book section that I'm covering. It teaches you how to iterate like a grandmaster on this competition. And this notebook is again by Jeremy Howard. If you end up reading through it, remember to upvote to support the authors. So this competition had the challenge of identifying similar phrases in US patents, and that was the end goal, to identify phrases that are similar. This is helpful because if you've ever I don't think anyone ever reads any technical jargon outside of their employment contract, but if you do, it's like really easy to mix a lot of things up and you could have one word that is like similar to another. And this becomes challenging when you're filing patents, right? Because you could spin the language off into like weird tangents, and it's hard for a normal human at least to be able to tell if it's similar to an already filed patent. So the goal here was to see if a newly filed patent is similar to another one. And for that, you had to figure out a way using transformers, most likely. Although there was a trick in this competition, which won't mention, that was just how the data was set up. But you had to figure out how similar are two different phrases. How do you get that character off and it's not the same? So that is, Pastor, I assume you're working with a different model. So whatever model was initialized there, I'll reopen that tab. I think it was a bird base. No, it was a Deberta if I remember correctly. So if you load in a Deberta V3, off would become tokenized like that. Can we use the same key for two different attributes in layout, in annotation? I don't exactly understand your question. So if you could please elaborate on that. How many patterns do I have? I have no patterns except for this RGB design. I'm just kidding. I don't. Uh, so inside this notebook, you learn how to participate in this competition and two of the important skills: creating an effective validation set and iterating rapidly to find changes which improve results on validation set. Murli says he's working on something similar. I was just catching up on that. That is cool. You can just probably take this notebook and speed your process up. But inside any Kaggle competition, and I don't mention this just as specific to Kaggle, but if you've ever competed, you will attest to the fact that this is very important outside of it as well. So for general machine learning workflows, it's really important to know how well your model is doing. For that, it's important how you set up a validation set. And secondly, it's important to be able to iteratively improve upon that and know how well you're improving. So that goes back to the first step. If you can do these two things, you can try a lot of experiments, find what works and what doesn't. And inside this notebook, we are shown different ways to create an appropriate validation set and taught how we can set that up. So we take a look at Pathlib library, which is awesome to load in stuff. If you're new to it, I would just suggest spending some time with it. That allows you to basically just load in stuff like that, and it makes your life a little easier, especially when working with all these long path lengths and all those strings where you can like mess up a semicolon, sorry, not a semicolon, a slash, and things don't load and you realize it later. Uh, Pathlib makes it a bit easier. So we take a look at the data set, and inside it, you have anchors and targets, and you have different scores of how similar they are. You're also given context. Think of this like, let's say A47 is chai, and then you have these two words, and you have to find out how similar they are under this context. Similar, I assume this would be wood. Let's say, I don't know for sure, but maybe wood is B44. So, under wood being a context, how similar are these two words? That was the goal of this competition. So, in such a case, how do you set up your validation strategy and how do you evaluate how well your models are doing? That is what this notebook teaches you. So, we take a look at how many anchors exist and how many numbers of them are there. So, for some reason, this particular anchor has the highest number of instances, and the smallest one is also somewhat similar, at least to me in like the 1 second I read it for. And you can see that there are a fewer unique values, and again, they're very short. So, you can also take a look at context and how many of them exist. All of this is important because it plays into how you will set up the splits for your data, and it also plays into your strategy. So let's say if your data set is highly imbalanced, what you'd like to do is do metric learning or perform arc phase or apply arc phase loss. We had looked at it last Sunday, and we had also looked at it in hydrogen torch, but that's what you'd like to do in such cases. So it's really important to look at the data. Many times you can just start, build your first model, and then also look at the data. If it takes like less than 5 hours to do that, that's what I like to do. But many experts start by looking at the data first. So whenever you're given a new problem, it's a good idea to look at the data set. And then you can plot also, because visually it gives you a nice idea to look at this. We can take a look at the score distribution, and we can see perfect matches are the least, and this follows this a bit of a bell curve, not the perfect bell curve, but a bit of it. And for some reason, at least in this plot, there are no zero point 0.4 scores. I think that might be a mistake. I might be wrong about that. It might be a mistake because I assume some scores might be zero point 0.4. So after printing out and after doing all of that, we conclude that we can see that these are just minor rewordings of the same concept and isn't likely to be specific to any context. So after doing this, based on this insight that we've gained, we can assume that okay, any pre-trained model should be pretty good at finding these already. That's the assumption we're going with. And we're going to validate that assumption with our score. Abror is pointing out the scores are like so. Thanks, Abror. I didn't know that. I have live streamed thrice about it and I keep forgetting. So now you know. My working memory is bad. Sorry, my long term memory is bad. Um, so we'll import all of the standard stuff. We're working with transformers. We're using the trainer class. Um, we'll take a look at what's a better class than trainer, and I'll have Zach Mueller present it. But accelerate is really good for later on, and that makes your life easy if you have a lot of GPUs and want to like make things easy for yourself. So what we are doing here is we're doing sequence classification, and we'll also import the auto tokenizer class. And for our backbone, we're using Deberta V3 small. This is my favorite model, and this is a lot of Kagler's favorite starting model, just because it's like very versatile, works really well. Uh, I spent a lot of compute hours on this, probably more than 5,000. But I think Deberta family is like one of the best starting points, depending on your use case. So when would this not be a good assumption if you're working with, let's say, if you have a lot of foreign languages, you'd want a model that's also been trained on multilingual data sets. So there XLM or XLM Roberta might be a good idea, which is also how it's presented in the fourth chapter. PyTorch Lightning for life. To each their own, I guess. I think FastAI also makes your life a bit easier when you're starting out. So we need to combine the context anchor and target somehow. We've loaded in the data, we've like loaded in the tokenizer, and there's not much research as to the best way to do this, so you might have to experiment a bit. So to start out, you'll just combine them all into a single string, and the model will need to know where this starts and where different words start. So for that, we'll print out the separator token, and inside token, the tokenizer object you create, you can take a look at what all special tokenizers sorry what all special tokens exist. So this is one way of accessing the separator token. Now you can combine your inputs like so. So you provide the separator token, and this is important because to us, space means the words are being separated. But remember, we just looked at how tokenizers work, and for Deberta V3 small, this is how it understands you would separate out words. It doesn't understand that space means it's a different word after this. This thing in two braces tells it that these are two different words. Generally, we'll get best performance if we convert data frame into Hugging Face data sets. So for that reason, we'll convert them over. And that is what we do. After that, you create a function to tokenize your data. And then you can take a look at how it looks like after being tokenized. Many a times, I would skip this, but this is somewhat important. And this is why I really like notebooks. So whenever you're like loading in stuff and doing a lot of things, Ayushman just saw like a really good piece of code I had written yesterday, which involved using bash script inside a notebook and doing fancy stuff with it and loading it into a data frame. But whenever you're trying to do something interactively, it's a good idea to see if it's loaded and if it's giving the output that is expected. So when you do this, you're not just looking at these numbers, you're looking at, hey, did it like load the thing it was supposed to correctly? And that's why it's like a good idea to always do that and always print that. So let's catch up on the chart. Why Deberta and not a smaller model? Bharat, I think like Deberta is a good baseline for me. I don't know, like Deberta small is like a small model for Kaggle, I would say. Abror agrees that the Deberta works best. If I'm learning deep learning, should I learn PyTorch or PyTorch and FastAI both? You should learn deep learning and you should figure out which frameworks make you learn the fastest. For most of the people, I know it's FastAI, but I was laughing at Ayushman's comment. Most of the people I know it's FastAI, but it also depends on you. So if you want to learn deep learning, figure out what makes you learn it the fastest. There are multilingual debater called mdebater. Let's take a look. I didn't know that. Thanks, Nischay. Mdebater. Oh, this is cool. I didn't know of this. Multilingual model can perform natural language inference on 100 languages and is therefore also suitable for multilingual zero shot classification. This is cool. I didn't know that. And I assume this is German. I guess I'm just guessing. And from there, you like performing zero shot compute and assuming that it's politics. Cool. Thanks for that, Nishit. Is the input from the data frame the same as the query? In what context are you asking this, Pastor? I should be banned from using Jupyter notebooks. When looking for correctness of inputs in between neural networks, like attention mask, how do you identify something is wrong? So, some obvious ways. Where did that go? I always lose my scroll for some reason. Here it is. So if all of this is zeros, that means like it's off. If all of this is ones or like some weird numbers, uh, it means it is off. Or if your the famous error where your training loss becomes not a number, then you have to just drink chai and pray that things become okay. But like if something looks fishy, it probably is. And like at an initial stage, if you're looking at input IDs, they should be different, for example, right? Not the like best answer, but you start to get a feel of how these should look after doing this a bunch of times. The new variable we just created, df input, when we pass it to the model, is the same query. No, that is not the query. uh, I'll explain all of this for a second. So we talked about q, k, and v, these like query key and value pairs that basically make these models work. And inside this, you have this nice representation of how keys and values work. And there's a query that gets sent, and you get the value after doing matrix multiplication. These are really high dimensional matrices. Sorry, I wasn't sharing my screen, I guess. So this is what happens inside the model. We assume that query keys and values get sent, and you get the value from matrix multiplication. These are really, really high matrices, high dimensionality matrices, and there is no way to know what those numbers mean. So we work with the assumption that when we do the dot product between these certain embeddings after pre-processing them in a certain way, the matrix you'll get in return is representing the value. Now, many people have analyzed that, and the researchers that put out the paper looked at that, but there's no direct way of sending a word to a transformer getting a return. Even when you're calling the Hugging Face API, a lot of this thing is being done in the background, but you can't just like download model weights and like write a query to it. A lot of operations happen behind the scenes. I don't know if that answers your question, but query keys and values all are like really high dimensionality matrices. They are getting values from all of that, and when you're performing these actions, it's sort of learning these things. That's the promise of deep learning, where it figures out all of this. And it's so versatile. It's so versatile enough that even for this competition where you're working with like legal data set, this one, it can somewhat figure it out by itself and work with that. I hope that made sense. Validation strategy for vision transformers, the same would apply to it. My good friend Vadim is back. Great to see you, Vadim. Vadim usually just gives us his time for Kaggle stuff. So I'm happy to see him join the other streams as well. So now the only bit we care about at the moment is input IDs. And we can see the tokens in the tokens that it starts with the special token 1, which represents the start of text. And then has our 3 fields separated by the separator token. We can check the indices of special token IDs like so. So if you go dot all special tokens, you can see all of them. Padding means it's like empty space that you mean to pad. This is unknown, this is masking, and this is CLS token. We learned about CLS tokens, so I won't go back to it. And this is separator, which is what we're working with. We can now tokenize the input, and you should ideally always batch it to speed it up. And you can remove the columns that you no longer need. So this becomes our data set for tokens. And then we can take a look at the first item. So to answer your question again, I think it was Akshaya. You should be printing this out, and now you know what this looks like. So when you get an output where attention masks are like all random numbers before even training your model, that means something is off. So again, re-answering your question. So now there's some analysis done on how the test set is set up, or some discussion was done. So based on that, what you do is you randomly shuffle the anchors by calling np.random.shuffle. And again, you would print this out to make sure like it's the right thing, right? So that's why you look always printing out stuff. And now you can pick 25% of these anchors to go in the validation set. So this is the most straightforward split you can do inside the Hugging Face API. You can like also pass all of this as a function, and it's usually like the argument is underscore frac, which means fraction that you want to like set aside as validation set. Most libraries, in fact all of them, should have this function to set aside like a percentage of your training data. How numbers in the text are tokenized? No, abroad we were looking at numbers after being tokenized. So those numbers represented words. Numbers are also tokenized in the same way. So a number would have a corresponding number representing it. And the neural network would be trained in a way where it knows that, I don't know, 50,240 means number zero, something like that. After this, you're set to like put this into a dataset dictionary. And you can create your first initial model. So this was the particular metric inside this competition. This is how it was being evaluated. That is why we defined this. And then we can set learning rate and batch size and weight decay and epochs. If you read this notebook, Jeremy actually suggests that pick batch size that works best for your GPU. For this is like a practical tip for Kaggle competitions and language models. Batch size really affects the accuracy, the third digit accuracy at times. So what you should be doing is like optimizing for the number that gives the best accuracy, which usually is like 16 or 32. So if you can use gradient accumulation, use any trick you can, use bits and bytes and 8-bit Adam. But these models tend to be sensitive to batch size as well. And on Kaggle competitions, you really sometimes care about the third digit as well. So after this, you can create a trainer and pass all of this. So if you actually end up reading through this, these are somewhat standard API calls. So I'm skipping past them. One pro tip, not trip. Remember to set this to true. You can never go wrong with this, because even on older GPUs, this will not give you any speed up, but on newer ones it will give you speed up. And even if you set it to true on older GPUs, you won't get an error. So as a default, I always like set this to true on Kaggle as well, where you like don't get a speed up, but then like it's for me to not mess up locally. Is higher batch size usually better? No, not in the case of language models. They are sensitive. So like if you go really high, they like start to, I don't know if they decay in performance, but there's like an optimal performance around a batch size number. So now we can create our model and finally train it by calling trainer.train, and this will get our model. Now we want to iterate on this. So you got your first score and you know how it's performing. You got your validation loss, you got your metric. But to like improve on this, you need to know whether the model is giving stable results. So for that, you can retrain it many times and see if it gives like similar results. So that's a good way. And if you read through the notebook, inside it, after this, we learn how to set up a k-fold validation, which is known as cross validation. So inside this, you create separate folds. I like to think of these as like separate parts or subsets or buckets of the data. So inside this, we have like n number of folds, which in this case is 4. And there are some fine nuances on how these work. So if you are new to it, the sklearn documentation gives like one of the best explainers on this. But basically, you like chunk your data into all of these buckets. So this is a simple key fold where you have these like four buckets. Yes, and the classes are divided like so. Stratified works slightly so differently. Stratified group k fold works slightly so differently. So you should know when to use what. And after doing this, you can also evaluate on models across these four folds. And I would suggest you can read the notebook from here to understand how that works. What you ideally want to land towards is after your initial pipeline is working, create a nice cross validation setup where you have like four, five, sometimes 15 folds, and iterate on your score from there. So that's what I wanted to teach you from this notebook, how to set up your CV. And this, I think, applies to any problem whatsoever, NLP or not. If you want, consider reading this notebook. After this live stream, I'll link it under the like button. So if you're watching this later on, you can just check out the link. Otherwise, search this on Kaggle and it should take you to the book, the notebook. Now I'll try to do a run of the transformer architecture implementation, and let me just catch up on the chart. Do we have early stopping for best accuracy? I think it exists in Hugging Face, Trainer, and Accelerate. Abroad, I would say just load up a tokenizer and tokenize the number two. See what you learn. Stratified is useful in imbalanced data. Yes, that's correct. I will put the link to the documentation I was referring to. Is this competition accepting late submissions? I didn't check. Let's see. So for those that don't know, usually a Kaggle competition happens for a while. So this happened 8 months ago, and after it's done, you can still make late submissions. I don't think it's allowing this. Is it? No, I don't think it's allowing it. Doesn't look like it. You didn't want to look at those submissions. I'm not sure about that, Pastor. I'll try to check after the live stream, but looks like it's not accepting it. So usually, if the competition accepts late submission, it's a great idea to still submit and see, because that allows you to check how well are you performing against all of such people. For example, this is the AI for code competition, and you can take a look and see where do you land. Cool. So now what I'll try to do is I'll try to do a run of this notebook and explain all of the parts. Last week we had taken a high level look at this, and since I don't want to mess up, if you see me looking down, I'm just referring to my notes inside the book and I'm just making sure I'm covering the things I wanted to. So this is how transformer architectures work. You have this part that is encoder, this is decoder. We looked at this last week, right? And we are passing the word, the sentence, time flies like an arrow. This gets tokenized, it gets passed to token encodings, which creates token embeddings. After that, you create positional embedding. Why do we need positional embedding? Sorry. This is one of the questions I think I have somewhere here. Yes. So these are like the kind of questions you'll see on the forums later on. But the reason we need this, once I find it, is you have all of these tokens that are created and these make sense to the model. It has an understanding of it, but it doesn't know yet what does it mean inside the sentence and how does it correlate to other words. So for example, flies, as in the book they keep telling you, flies could be like an aeroplane flying, it could be a house fly, it could mean anything. So this positional embedding sort of encodes this information and tells the model, hey, it's in context to these words and it's supposed to mean something. After that, this gets encoded, it gets converted into hidden states, and these get passed as key and value pairs to the decoder. There, the same thing happens, and from there, you have the final predictions coming out. There's one more cool thing being subtly pointed out here. You can simply have all of this model, which could be a transformer backbone, and on top of that, you can train a head which can learn different things. Inside the encoder, this is multi head self attention. One thing worth noticing is you have all of these feed forward networks looking at individual embeddings, and the size will remain the same as input. I was just looking at my notes for that. The reason for that is because all of these are somewhat feeding the contextual information and positional information to them. So the size remains the same, but they slightly so alter all of these inputs to have more info about the neighboring stuff. And all of these encode all of these things. How do we know that? We know that through practice. We don't force anything, we don't force the embeddings to learn some uh, meaning, etc. It just learns by itself. So we are not teaching the model how to learn it, it encodes that information by itself. Again, to point that out. Time flies like an arrow, fruit flies like a banana. That's a good one. Yes. So this is happening inside the encoder block. And this is what self attention looks like, which can be done with the scale dot product. We had looked at all of this last week, and we had also looked at how different words connect to other stuff. So time is connecting to time, fly is connecting to all of these words. We can take a look at the last layer, and I think there was a cool question by someone which we had gotten confused and figured out. So flies should arrow should connect with the last token, which it did not. And then we figured out after going to the last head that it does. So if you go to layer 11 and head 11, you can see that arrow connects to the final token. I had somewhat already mentioned. Is this font size good enough for everyone, or should I zoom in a bit? I'm asking about the code. If someone could please confirm. I'm just waiting for someone to write in the chat. I'll still zoom in a bit just to be sure. Fully saying it's fine for him, so I trust him. Cool. Others are saying fine as well. Thanks, everyone. So the whole concept of self attention is I'm reading from the book. It's a weighted average. The whole sequence is used to compute a weighted average for embeddings, and this basically tells the importance of different words to it. And instead of fixed size embedding for each token, we use the whole sequence for an average of each embedding. And we have just taken a look at how that works. But that is just self attention. After this, we take a look at how multi-head attention and scale dot product of attention works. Les is saying that's where the original sentence came from. I didn't know that. Thanks for that. I think he's talking about time flies like an arrow, fruit flies like a banana. Thanks for that. So I'm reading from the book now, but there are several ways to implement a self attention, and the most common one is a scale dot product where you project the token embeddings into three vectors, compute their score, and compute their weights. So, four steps: project them into vectors, compute their scores, compute their weights, and update their embeddings. So, here we import again from all of the vanilla stuff. We set NN embedding here, and this is one of the questions. Les said I should zoom in a bit, so I'm zooming in for him. We are creating embedding instead of a one hot encoder, which is what we did in the first or in the previous live stream, because now it's not just a one hot encoded vector. This would be carrying details for 30,000 different contexts or 30,000 different embeddings. And that's because this would be a sparse matrix consisting of vocab size and the hidden size. So vocab in this case is this big, and there are 768 such tensors. We can also take a look at the input size. So this is one, which is the size of the batch. This is the sequence length, and this is the hidden state size. After this, the authors flex their knowledge of PyTorch. So we had looked at the four steps. To perform that, you need to do a batch matrix multiplication, and you initialize the query key and value to the same size as input embeds. You set the dimension of keys, and then you compute the scores. So you do that by doing torch.bamm, which is batch matrix multiplication between query, and the transpose normalized by dividing it with dimensions of key. And from there, you get this tensor, which is of size 155, which means you're getting five scores, right? And BMM again is matrix multiplication. After that, you apply softmax to somewhat smooth this out, and you finally get the attention output by doing a batch matrix multiplication between weights and value. If this didn't make sense, you can scroll up to here and it will start to make sense. So what you are doing here is you're doing a matrix multiplication or a dot product between query and key that you end up scaling. You apply a softmax to smooth it out, as the authors say. And finally, you do matrix multiplication between the output of these and the values. So you do a scale dot product, and finally you return the product of weights and values. What's going on inside this function? You set the dimension of k like we had earlier. You again compute the scores, you compute the weights, and you return this value. So far we had looked at how these individual pieces come together, and then finally we had combined them inside a scaled dot product attention function. So I had shown my face and pointed out those four functions. I will read them out again and you can see them happen here. We project each token into three vectors. We compute their attention score. We compute their attention weights and finally update the token embeddings. That's what's happening inside this para of code. We are running out of time, but I'll still try to cover this. So it might go overboard. If you had commitments outside of the hour, the video will remain up. But I'll try to cover multi-head attention. I'm just reading up to make sure. And one of the questions I had is, why do we need several heads for multi-headed attention? That's another question I'll point out later in the week. But the answer to that is the softmax of one head that we had looked at earlier in self attention just focus on one aspect. But if you apply multiple heads and multiple soft attention, that allows the model to focus at multiple different things, if that makes sense. So that is why multi-head attention is usually a good idea or a better idea. So inside of here, we'll follow somewhat similar steps, or we can just take a look at the implementation. So you have query keys and values going into these linear functions, after which you do a scale dot product attention, you concatenate them, and these are passed through linear layer. So now we create this attention head where we initialize based on the neural nn dot modules constructor, assign query keys and values based on these dimensions, so embedding dimension and head dimension. Define the forward function like so. So attention output is the scale dot product attention, scale dot product attention, and we had just defined this right from earlier. After that, you concatenate these. So you calculate the attention outputs and you're just returning the attention outputs here. Inside multi-head attention, you create the embedding dimension based on the hidden size. You set the number of heads. This is a hyperparameter. The dimension of heads is always this, so it's calculated like so. And the heads are combined in this. So you pass all of these and wrap around attention head function. You create attention heads, and the output goes through a linear layer. So let's say you have 12 such layers being passed through. All of them will be wrapped around this attention head function, which will do these applications, or it will convert them into an attention head wrapped class object. Finally, you'll perform the forward class. So we were missing the concatenation from earlier. And we'll do a torch.cat where we'll combine all of them, and the output will be a linear output. From here, you can call multi-head attention on the configuration you care about, and you can pass in the input of embeddings. And this is just for checking, but you'll again get the same size as earlier. And you can sort of visualize this and see how it works. So let's take a look at how attention is being paid here. I think because of zooming in, it's like acting weirdly. If I zoom out a bit, yep, there we go. I'll zoom in again, but just to point this out, you can take a look at how this multi-head attention behaves now. So, Kuber, this somewhat answers your question, I assume. But multi-head attention allows the words to pay or to be connected to different things as well. So, let's say if we look at the last layer, we can see that flies is being connected to itself if you're looking at the same sentence. But if you look at the mapping from sentence A to B, we can see how these things are connecting. I don't know if that answers your question, Kuber. So after this, we add normalization layers. Why do we do this? This is how the thing exists. So there's no reason. You could probably experiment and see if you can come up with a better approach. Most likely no, because many people have done that, and many transformer model already exist. But the reason we do this is because this is how it exists. This is how it's been defined. So we are following this uh, approach now. We looked at individual functions. So the first thing we did was we looked at what self attention is. Then we looked at multi-head attention, and now we're like trying to get to a transformer based architecture. So we're zooming out constantly, and we're like trying to put all of these pieces together. So now you have the following functions being done. You could either have a post layer normalization, and you have these skip layers. So if you're familiar with resonates, the word skip layer comes from there, which means basically this input gets skipped over whatever module was here towards the next input, towards the next module. So you have the inputs going into a multi-head attention, you have a skip layer. After that, you could do a post layer normalization, and from there it gets fed to a fully forward neural network. You could also have a pre-layer normalization, and you could have a layer norm before you do all of this. This is how these are defined, and there's no special reason for that. Similarly, using GELU is conventional here. So what we like to do is use this activation function because it works the best. And this is how we define the final feed forward layer. Sorry, the feed forward layer. And again, after doing all of this, I skimmed past it because I assume everyone knows how this is being set up. But the size remains the same. So as we keep zooming out, we just want to make sure, and that is why we are paying attention to the sizes, because we want to make sure it's like not something that we're deviating from. But when we started out and started individually implementing these pieces, we looked at the tensor size, and then we are like creating functions that still remain somewhat same, and the dimension remains the exact same. Now you can create the encoder layer, and we can pull all of these functions together. So we have defined feed forward earlier, we have defined multi-head attention, and we have layer norm, which is predefined from NN module. We put all of these together, we define the forward function where we apply layer normalization, and this is the skip connection being done. So you have x plus self attention hidden state. If you look above, if you call this x, you have x plus attention being fed to layer norm, right? And finally, you can grab the encoder layer and take a look at the embedding sizes. Let me just catch up on the chart. The output from MHA is updated embedding that is same as the value. Ebror is saying resonates. I'm just trying to read it to make sense. Output from multi-head attention is updated embedding that is the same. It's the updated embedding for values. Is that what you mean? Sorry, if you could please clarify that. I'm assuming you made a typo there. So if you're asking about positional embeddings, they get created afterwards. I was just reading my notes to make sure I remember it correctly. So far we managed to encode all of this data to the model, but now we need to figure out a way to tell it how different things have been encoded and what the position means, as we have been discussing earlier. So we do that by creating this embedding class and passing it in all of this information. We have already defined why we are using nn dot embedding and not one hot encoded representation. So I'll skip past it. So you define token embeddings, you define position embeddings. You of course create layer norm and invite dropout. Inside the forward function, you grab the sequence length based on the sizes first. What's the right word for it? Size would be a matrix, so you'll just like grabbing the first dimension of it. You create position IDs like so. So you unsqueeze sequence length and arrange it. Oh, sorry, not arrange it. Torch dot arrange does the following. Returns a 1D tensor of size like so. This is being rendered in. I was trying to see in the YouTube live stream if it's being rendered like so. Yes. If you go to the documentation, it will render correctly. But we are creating a tensor based on this for position IDs. And from there, we create token embeddings, position embeddings, concatenate both of these, normalize it, and apply dropout. Why do we do all of this? And is there any logic for combining these? That is just the definition of how the architecture was defined. Inside the book, you will find text explaining why we do this and how it works. If you are trying to think how they came up with this and where did the intuition for that come from, this is how it was defined. So if you read the paper, you'll find all of this stuff. And you can again take a look at the size, and we are putting all of these pieces together. So now we've added positional encoding, and still we have our cute little one sized batch with 5 sequence length and hidden size 768. So now we can call transformer encoder like so, where we grab the embeddings and create the layers and simply define the forward function like so. So we create self embeddings and pass it like so. Finally, you can also add a classification head. This is straightforward, so I'll skip past it. One thing I'll point out still, this is how you define the CLS token. And if you are implementing this from scratch, or if you are implementing this without looking at the notebook, this is where I mess up most of the times. And you have to pass the CLS token like so inside the encoder. Select the hidden state of the CLS token like so. So after you've defined this transformer for sequence classification class, you can define the number of labels and you can pass this configuration, and it should allow you to basically do classification between three such classes. That's the end of the notebook. So what I'll do is we'll come back to this notebook, and I sort of glanced over a bit towards the later half since we had run out of time. But we'll again revisit this and wrap up this stuff. I meant to cover multi-named entity recognition as well, but I think we'll again defer that to the next live stream. We're also looking at text generation, so I wanted to cover this paper. I have read it, it's quite cool to see. This is now the largest open language model, and I'll try to read this paper to somewhat break all of you into reading papers as well. If you read papers already, please excuse this, but I assume this might be helpful for a lot of you. This was by Facebook AI, and this is already really popular. So we'll take a look at what this is in the next live stream. We'll take a look at multilingual, and we'll wrap up our understanding of transformers. So I glanced over a lot of things, but to re-summarize, we looked at how self-attention works. We looked at how multi-head attention works. Then we kept putting pieces together. We learned how positional encoding works, how the architecture is defined. We kept adding those pieces in code and kept looking at the dimensions. And towards the later half, we still remained the same. The dimension remained the same, which means we were like getting closer and closer to implementing this correctly. Finally, we added a classification head for three classes, and we were able to create this transformer for sequence classification. So we'll wrap this up next week and continue forward. I'll answer Pastor's question now. If the values are the same as the updated embedding, I think it's slightly different. So that is not the embedding we are being returned. Les is saying thanks. Thanks for watching, Les. All right, everyone. I'll wrap up here. If you haven't already, please consider subscribing. I'll point some homework out for everyone. And Pastor, if you don't own a copy of the book, I'm happy to basically assign the giveaway to you. So this will be a digital copy. If you don't have the copy, please reach out to me anywhere with your email, and I'll send the copy to you. So for homework, try to improve on Jeremy's notebook. Someone pointed out, I think it was Abror pointed out, you can't do late submissions. So just take the notebook and see if you can improve the CV. So I didn't know you can't submit to it. Implement multi-head attention without cheating. So please take a look at this notebook, not to all the cells, shift enter through it, come back to it, close it, and then try to implement it without cheating. That's it for homework. I already said what we'll be looking at next week, and I'll see you then. Make sure to try Tashkent chai as well. I haven't. I'm down to try any chai at all. Cool. Thanks for watching, everyone. I'll see you all next week.